Hello, and welcome to our lesson on parallel vectors. Today, we will delve into some fascinating concepts that will enhance your understanding of vectors and geometry, ultimately improving your problem-solving skills. In this lesson, we'll build upon your existing knowledge of vectors and compound vectors by introducing the concept of parallel vectors. Our primary focus will be on understanding and identifying parallel vectors as well as using them in various geometric arguments. We will proceed as follows. First, we'll clarify what parallel vectors are and how to recognize them. We'll then discuss how to use this knowledge to form and solve geometric arguments. Finally, we will examine several examples and cases to apply these new skills. In our previous lessons, you've successfully grasped the basics of vectors and compound vectors. You should understand how vectors are represented and added together to form compound vectors. With this solid foundation, we can now introduce the concept of parallel vectors. For example, consider a situation where you need to determine if two directions are aligned, perhaps to find a common trajectory in physics problems or to analyze the direction of lines in engineering designs. Recognizing parallel vectors simplifies these tasks by providing a clear method to compare directions and orientations. To understand parallel vectors, we must first know what vectors are, so let's recap some of our previous learning. A vector is a quantity that has both magnitude, which means length, and direction. You can imagine a vector as an arrow. The length of the arrow represents the magnitude of the vector, and the direction the arrow points in represents the vector's direction. When writing vectors, we often use a letter with an arrow above it or just a bold letter. Vectors have components, which are their values along the x-axis and y-axis in a two-dimensional plane. For example, the vector v could have components vx, vy. Now that we recapped what vectors are, let's talk about parallel vectors. Two vectors are parallel if they point in the same direction or exactly opposite directions. Mathematically, if you can multiply one vector by a scalar, which is another term for a constant number, to get the other vector, then those vectors are parallel. When multiplying a vector by a scalar, you can simply multiply each component of the vector by the scalar. For example, to multiply the vector a equals 2, 4 by the scalar 2, you get 2a equals 4, 8. For example, let's consider two vectors a and b. Notice that you can multiply vector a by 2 to get vector b, which equals to 2a. Since b is 2 times a, the vectors a and b are parallel. They have the same direction but different magnitudes. So, to determine if two vectors are parallel, you want to check if the vectors point in the same direction or exactly opposite directions. See if you can write one vector as a scalar multiple of the other. Let's go through some examples to clarify this further. Consider vectors c and d. Since d equals 2c, vectors c and d are parallel. Now consider vectors e and f. In this case, it is not possible to find a number k such that f equals ke, so the vectors e and f are not parallel. To check this, we can compare the ratios of the x and y components of the two vectors. We will explore this further in our worked examples. Parallel vectors come in handy when proving geometric properties like the parallelism of lines and collinearity of points. To prove two lines are parallel, we can use their direction vectors. Let's say line 1 is represented by vector g and line 2 by vector h. If we notice that h equals 0.5 times g, then lines 1 and 2 are parallel because their direction vectors are parallel. To prove that points A, B, and C are collinear, which means that they lie on the same line, we can check if vectors A, B, and BC are parallel. Suppose points A, B, and C have the following coordinates. To find vector AB, we need to find the difference between the x-coordinates and the y-coordinates of A and B. The x-coordinate of B is 3 and the x-coordinate of A is 1, so we find the difference to get the x-component of the vector is 2. We can do the same for the y-coordinate to find that the y-component is 4. So we find that vector AB is 2, 4. Now do the same process for finding the vector BC, and we find that vector BC is also 2, 4. Since AB and BC are the same vector, they are parallel. This indicates that points A, B, and C are collinear since they lie on the same line. Suppose we have a quadrilateral ABCD with the coordinates shown. We want to show that vectors AB and CD are parallel. The vector AB points 4 units right and none upwards, and the same is true for the vector CD. These vectors can therefore be written AB equals 4, 0 and CD equals 4, 0. Since AB equals CD, vectors AB and CD are identical, so they have the same magnitude and direction. Because they have the same direction, they are parallel. Let's walk through another example. Look at the diagram of two translated triangles. Triangle PQR is translated to form triangle P'Q', R'. We want to show that the vectors PQ and P'Q' are parallel. We calculate these vectors by finding the change in x and y coordinates for each vector. We find that vector PQ is 2, 3. And that vector P'Q' is also 2, 3. Since PQ equals P'Q', the vectors are parallel and also equal. This should be expected since translation does not affect any property of a shape other than its position in space. Let's do a final example. Consider vectors C and D, where C equals 3, 9 and D equals 6, 18. Let's check if they are parallel. We calculate the ratio of the components. For the x components, we do 6 over 3 and we get an answer of 2. For the y components, we do 18 over 9 and we also get an answer of 2. This gives us D equals 2c, so vectors C and D are parallel. These examples demonstrate the process of identifying and using parallel vectors in geometric arguments. Remember, the key is to check if one vector is a scalar multiple of the other. In today's lesson, we explored the concept of parallel vectors, a key idea in vector geometry. We began by recapping what vectors are before understanding that parallel vectors are those which have the same or exactly opposite direction, differing only by a scalar multiple. We then moved on to identifying parallel vectors by examining their components. By ensuring that the ratios of corresponding components are equal, we can confirm that two vectors are parallel. We also discussed the geometric implications of parallel vectors, noting that they can be used to show that two lines or segments are parallel in a geometric figure. This is often useful when dealing with shapes like parallelograms and trapezoids, where parallel sides are a defining characteristic. Finally, we applied our knowledge by solving problems where we identified parallel vectors and used this information to make geometric arguments. By mastering the concept of parallel vectors, we can simplify complex geometric problems and gain deeper insights into the structure and properties of various figures. This foundational knowledge will be an asset as we continue to explore more advanced topics in vector geometry.